though for water, we do say a submarine going down will get bigger pressure and will be crushed when you are going down in the water. But when you go up in air, the air at here and the top of this building is similar. The pressure is similar. But if you go into high enough mountain, you can feel the pressure difference of air. Or if you take a pen, and as you go up, you will feel something funny about your ear. That's a pressure difference of air. So when you move high enough, there's going to be pressure difference in air, but at this scale is negligible. Okay? Good. So even though the air pressure down here and up here is similar, we can change the air pressure by using a vacuum. If you are using a straw to drink your boba, what happens is that the air in the straw and your mouth so your mouth is creating a cavity. There's air in here, and this is water down here in a straw. So what your lungs can do is you can remove some air inside your mouth to decrease air pressure. You remove the air particle. So the pressure in your mouth, even though it comes from some air, will be smaller than the pressure of air out there. So the air pressure at here is similar, but the air pressure inside your mouth is different because your mouth is isolated from the exterior air. It is your lungs, your mouth, and the straw. The air inside your mouth and the air in the air is not connected, so they can have different pressure. Now, when I look at this height, the pressure is air pressure. Let's say this is P1. And when I go down, the pressure increases. But when I go up, pressure decreases again. So the pressure at the same height for a static fluid will be the same. And according to that formula, the pressure difference between 2 points, 2 locations, depends on the water height. So when I look at P3 up here, which should have the same pressure as the mouth over here, because inside the same air, the pressure difference is similar. So P3 should have the same pressure as your mouth, and P2, P1, and P air are all the pressure, are all equal to the pressure of the air. Now, yeah, Olivia?
How come the P3 equals
P3 is in the straw, so it is contacting the air in the mouth.
Oh, okay.
Any other question? Okay, now, when I look at the pressure difference between P2 and P3, which one should have bigger pressure? P3 should have bigger pressure. P2 should have bigger pressure. Let's think about it again. Imagine you are a small diver, start diving from P3 to P2. You are going deeper into the water. There's more water on top of you as you go down to P2. So which one should be bigger, P2 or P3? P2 should be bigger. Okay? So when I use this equation, I'm just going to write P2 will be P3 plus a positive number, which is rho g, and let's say this is the height of the water in the straw. So P3 is the same as the pressure in the mouth. P2 is the same as the pressure in the air, and that will be rho GH bigger than the pressure in your mouth. You decrease the pressure inside your mouth, so the water will be pushed upward by the pressure of the air. So we know pressure of the mouth should be smaller, and indeed it is smaller. You need to add this number to the pressure mouth, to P mouth, to get the air. Okay? When you are looking at static fluid, going deeper will always increase the pressure. Izzy, do you have a question?
No.
Okay. So this is how I get the pressure difference from the height here. But usually when we're drinking a straw, we control the pressure in our mouth and suck the water up. So let's see how edge is related to that. I want to isolate edge, so I move mouth to the other side, and I get P air minus P mouth should be rho G H. I subtract P mouth from both sides. And I want to isolate H, so I divide both sides by rho G. And I get the height of the water I can suck up in a straw will be the pressure difference between the air in my mouth divided by the density of water and how big gravity is on Earth. So you can run a density check. If the water is heavier, which means bigger density, is harder to suck it up. Gravity is bigger, water is heavier, it's also harder to suck it up. So edge should go down if these two go up. It makes sense. Now, what is the minimum possible pressure you can create with your lung by removing air? The minimum possible pressure you can do is when you have no air at all in your mouth and nothing is bumping to you. So the minimum possible value for pressure in your mouth by removing air is 0. You can only decrease the pressure until 0 when there's no air at all. So there is a maximum possible value for the height of water rise in a straw that you can create by sucking the air. It's just going to be P air itself, when you set this to be 0, and divided by rho G. Now, this means that there's no air in the mouth at all, and what the air pressure is doing is just they push down the water so the water can rise up until the gravity or until the mass of this water column becomes so heavy the air cannot push it up anymore. So there's a maximum possible height you can push up just by the pressure of the air. Now, pressure of the air is 1 atm. Density of the air is 1,000 kilogram per meter square, meter cube. G is 9.8 meter per second square. If you do the calculation, this turns out to be around 10 meters. You can only drink your boba with a straw with a height shorter than 10 meters. If you can use a tube longer than 10 meters, come to the physics building, we have an empty space in the middle, and it's 10 meters tall. If you can drink water higher than 10 meters, I'll give you A+. Okay? So now, 10 meters sounds tall enough, but if you look at the trees growing around us, it's weird. We can only transport water on a straw until 10 meters. But a tree can easily grow longer than higher than 10 meters. This is a sequoia tree in Sequoia National Park. I went there right before I came here to teach you in the summer. This is me. Here, I am standing at here under the sequoia tree. So you can see that tree is so tall, way more taller than 10 meters. The 10 meter here is up to scale. You multiply 1.8 to like enough number, so that's 10 meters. So you can clearly see that the tree is taller than 10 meters. Now, with straw, you can only transport water up until 10 meters. But the tree needs water all the way up to the very tip. Every leaf on the tree needs water. Every cell of the tree needs water. So how does a tree transport water all the way up above more than 10 meters? Well, you can only do 10 meters with a straw. That's the thing I want to explain this fast. Hopefully I can make it. So just keep that in mind. There must be some other way to create pressure difference besides removing air. Now I want to talk about the last thing about just the road. I want to talk about the last thing for this formula. We get this rho g by looking at a system. And now we can use that to derive buoyancy. Buoyancy is defined as the force of water combined with the force of air. The reason that we do that is because we want to say when something is floating on top of the water, you know there's gravity going down, but it's not sinking. And we just say the thing canceling gravity is buoyancy. So we will define buoyancy in such a way that it cancels gravity right now. This is called buoyancy. But what's happening here is that the force from the water minus the force of air, because they are pointing in different directions, equals gravity. So you know buoyancy is actually the sum of the forces from all the fluid